Hello everyone, this is Subhashri here. In today's video lecture, we are going to discuss about small signal model of a diode. First of all, the very major important application of a diode is that it can act as a rectifier. It is mainly useful for building the rectifier circuits, so that it will reject either the positive voltages, that is allowing the positive voltage and removing the negative part, or either removing the negative part and allowing the negative part and removing the positive voltage, either of the type. So it can be classified as, we all know about that, either an off wave rectifier or full wave rectifier, or even bridge rectifiers also. N number of rectifier circuits are available, with which the major application of a diode plays a very important role over there. Characteristics of junction diodes. The PN junction diode can be operating under the forward bias condition. After the cut in voltage, the current will start to increase rapidly, but under the reverse biasing condition, after a particular voltage, there will be the sharp increase in the current takes place. So that means after attaining the breakdown condition, there will be the sharp increase in the current will be taking place. So that is the condition, that is the characteristics of the PN junction diode under the forward bias and reverse bias conditions as well. So under the forward bias condition, the diode will be acting like a closed switch, but under the reverse biased condition, the diode will be minus Is, that is it's like an open switch, that is off. And the diode current equation. So the diode current can be represented as I is equals to Is into e power V by eta Vt minus 1, where Is is the saturation current, that is reverse saturation current, the minimum amount of current which flows through the diode under the reverse biasing condition. So E is equal Is into e power V by eta Vt minus 1, where Vt is equal to Kt by Q. Vt is the thermal voltage, K is the Boltzmann constant, T is the absolute temperature, and Q is, as we all know, that Q is actually the charge. Okay, so with that condition, we know the approximate diode equation can be written as I is equals to Is into e power V by eta Vt. Okay, when the value is greater, when the value of current I is greater than Is, then we can represent the equation of diode current as like this. So under the reverse bias condition, the value of the applied voltage will be very much lesser than 0, which will be in the form of negative range. So that is the reason why the condition for the diode current will become I is equals to approximately equivalent to the value of the saturation current. So in breakdown, after attaining a particular peak value, the current will start sharp increase. So that will be taking place. So after attaining the breakdown, and then the movement of the charge carriers might be because of the movement of the charge carriers due to both the holes and electrons as well. These two are the two different mechanisms, that is the major important mechanisms are diffusion and drift as well. So diffusion is the process of making the charges to move from the higher concentration region to that of the lower concentration region, and which is due to the concentration gradient. And drift is the process of acceleration of the holes and electrons, acceleration of the carriers, and acquire the drift velocity. So because of that reason, the the current will be due to the drift that is drift velocity, the current density. And that is how we can relate the diffusion and diffusion constant due to electrons and holes as well. So because of that diffusion process, and we are relating the diffusion constant and mobility by using this Einstein relation, that dp by up equal to dn by un equal to Vt, that is thermal voltage. And we can have a look at this excess minority, that is a minority carrier concentration. If say for example, if we have a n-type region and p-type region together, n-type region we will have a majority charge carriers as electrons, and in p-type the majority charge carriers as holes. So the minority carrier will be additionally there in that type of a semiconductor whenever the diffusion process will be taking place. So that can be related, or that can be represented by this expression Pn of x of n xn equal to Pn naught into e power v by vt. Similarly, the distribution of this excess charges can be represented by Pn of x equal to Pn naught plus Pn of x, the same parameter which we have already wrote, minus Pn naught, that is under thermal equilibrium condition. This value of Pn naught represents the whole concentration, minority whole concentration under the thermal equilibrium condition. So where in this term, the e power minus x of minus xn by Lp, this Lp represents your diffusion length. So the average time which is taken by the charge carriers to inject into its before recombination, that is called as diffusion length. And diffusion of holes, which leads to the following current density expression. So Jp is equals to Q into dP by Lp into Pn naught into e power v by Vt minus 1 into e power the same term into e power minus x minus xn by Lp. This is the expression for your. So under equilibrium condition, we can represent the current due to the current density due to the holes and due to the electrons in this fashion. That is, by adding these two, we will get the total current of a diode current expression, that as I is equals to Is into e power v by Vt minus 1. So the first, we know the relation, that is incident relation. According to that, dP by Lp, here we can write the expression can be changed into Pn naught and Np naught. For that is for p-type semiconductor, the electron will be the minority carrier, and for the n-type semiconductor, the hole will be the minority carrier. So because of this reason, we will get the current density expression due to both electrons and holes as well. So by combining the two, we will get the expression as I is equals to Is into e power v by eta Vt minus 1, where eta is the ideality factor. So here the diode circuits, we have considered one of the basic diode circuit over here, and this is the characteristics plot of a diode, and we can find a Q point, that is Q point is also called as an operating point, where we can find the location, that is under this DC load line we can find a operating point. So after certain point, after a cutting voltage, the current will start to increase in the diode. Okay, so we have just before discussed about the diode equation, and this is what about your characteristics plot of the operating point, where we can find an operating point from this load line diagram. And coming to this diode small signal model. So diode small signal model, we are considering the basic expression as your diode current expression. With that diode current expression, we modify the slope of your current and voltage as well, because in x-axis we have considered the voltage and in y-axis we have considered the current. So while taking the slope, there would be some change in the voltage will be taken place, and also the change in the current will be taken place. So that would be the major point for calculating the parameter as resistance R, V by I. And then here we have to note down one thing, that the value of VD of t, that is the voltage across the diode, that is VD of t, is sufficiently small when we can expand the exponential and get an approximate expression. That is major important point for the small signal approximation. So exponentially we have to make the value to be expandable, that is it should be valid for VD less than 10 millivolt. That is the point. And here this ID of t is equal to ID into 1 plus VD by eta VT, and similarly that can be rewritten as ID plus this entire term represents your small ID, so ID plus small ID, which is whereas ID is equal to ID divided by eta VD into VD. This is the parameter for the small signal. So from this we can modify the value of RD as eta VT by ID, that is change in the value. Okay. Now finally, to perform the small signal analysis of a diode circuit biased with VDD by eliminating the DC sources and replacing the diode with small signal resistances. Okay, so finally the resulting voltage divider will be giving, this is what the circuit. Say for example, if we want to make the resultant voltage divider circuit, the opposite voltage, when we want to calculate the value of VD, the opposite voltage, that is opposite voltage Vs into opposite resistance RD divided by sum of the two resistances. So now separating out the DC or bias analysis and the signal analysis will be used as a one of the technique, very important technique. Small signal analysis plays a very important role. Thank you all.